Okay, welcome to the DDPS seminar, everyone. Before we introduce our invited speakers, let's go over some rules and logistics, the same rules and logistics I have been announcing every time we host the speaker in DDPS seminar. All right, first of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed. So please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me introduce our speaker today. It is an honor to host Sorin Mitran, who is a professor at the Department of Mathematics in University of North Carolina, Chapel Hill. He received his PhD from Polytechnica University, Bucharest, Romania in 1995. Before he joined UNC in 2002, he was a research associate at the University of Washington, Seattle from 1999 to 2002, and a guest scientist in Germany from 1998 to 1999. He authored and co-authored 9 books and chapters and more than 40 referred journal papers. Today, Sorin will talk about data-driven information geometry approach to stochastic model reduction, which is a very interesting topic, obviously. So please enjoy and expect a wonderful talk. Now, without further ado, let me pass the baton to Sorin by asking one random question as usual. Today's random question is, what is your idea of the perfect day? For example, you got the Nobel Prize, and that would make it perfect day.
No, the perfect day is a fair wind and me and my sailing dinghy out on the ocean.
Oh, that sounds wonderful. All right, the stage is yours, sorry.
Okay. Hello, I can't see anybody, so I can't be quite that interactive, but please do interrupt with any questions. If I understood correctly, the general atmosphere of this series of talks, it's more in the way of working seminars about ideas to approach these kinds of interesting data-rich problems.
Correct,
And that's the
correct.
way that I group these slides. So rather than focus on polished, published results, I want to kind of open up my workshop here to everybody to see if there's points of interest that we can collaborate on or things that might raise your interest. That being said, let me give an overview. We're going to be looking at first a bit of motivation on why I was led, after looking at a bunch of problems that involve stochastic microscopic physics, at the particular approach embedded in classical differential geometry, but with a twist, namely looking at the differential geometry of manifolds whose points are probability distribution functions. This is something which was pioneered in mathematics by the work of a Japanese mathematician, mostly Amari. And there was a great focus on analytical descriptions of such manifolds. My interest, based upon the physical motivation I'll be going into in just a bit, is in extending the analytical framework to a computational one that can be used in various types of applications. And I've picked 2 applications today that we can go into. One, a relatively straightforward application, and one a more involved thing from biomechanics. Motivation. We all went through school and learned classical physics. That's the way the world works. One of the interesting questions is, why does it work? Why is classical physics so successful? And of course, we have a pretty good idea that it all boils down to that one single fact of physical knowledge that Feynman told us we should hang on to if ever we come out of a nuclear cataclysm, namely the atomic hypothesis. Matter is composed of very small portions, atoms, that interact with one another. And the fact that they are so many in number allow us mathematically to apply the law of large numbers and the central limit theorem, The way that I like to think about this is that the law of large numbers tells us that even though we might have stochastic motion at some microscopic scale, we can define averages. Therefore, we can think that nature is rational. We can make predictions on the average behavior of something to be expected. We can measure things. The central limit theorem then tells us that if we have lots and lots of such systems that we measure, not only can we find averages, but we can furthermore describe in a very quantitative manner the deviations from those averages. And basically we have our familiar expression of going to a normal distribution of the deviations in measurement and something that converges with the inverse square root of the number of trials that we carry out. So in this way, nature is kind. We can do analytical averaging in the sense that if we introduce a Hermite polynomial scalar product and we have any probability distribution that comes about from microscopic physics, we can carry out those averages analytically and come up with macroscopic laws that we use all the time. This is perhaps most famously exemplified, of course, by gas kinetics. If you have n particles, let's say it's an ideal hard sphere particles just interacting by collisions, and you're interested in characterizing this gas, you can imagine that each particle can occupy a certain energy level at a certain probability. And keeping things discrete for a moment to ease the derivation, you have a bunch of constraints, actually not that many, just two. One, standard normalization of a probability distribution. All the probabilities have to add up to 1. They're all positive also. And a total energy. And the way that we can then come up with a Maxwell-Boltzmann distribution is something which is familiar from just classical statistical physics. We construct the H function or the entropy, and then invoke this hypothesis of molecular chaos to maximize the entropy and thereby come up with a Maxwell-Boltzmann distribution. Since this is something of Gaussian form, nature is kind. It allows us to integrate this and plug it in to things such as the Boltzmann equation from kinetic physics on the bottom there, and then come up with ways that we can derive our equations for macroscopic fluid flow, the Euler equations in the first approximation, Navier-Stokes in the second, Burnett in the third, and so on. So that's the overview of classical physics. Now, if we were to do a critique of this, you come across the following observations that, sure, if I'm observing things like a ideal gas at my scale, namely, let's say something 10 centimeters length scale, 1 second time scale, I'm observing the behavior of about 10 to the 22 particles. They're moving somewhere around the 500 meters per second, let's say 1,000. And there are, in 1 second, 10 to the 32 collisions. Even though we're kind of used to Monte Carlo simulations converging slowly as the inverse square root, if you're at 10 to the 32 realizations of your experiment, even that slow convergence gives you something like 16 digits of accuracy. So not only the law of large numbers and the central limit theorem are applicable, but they're very accurate. We get essentially something which looks like deterministic behavior. Any deviation from the deterministic behavior is something at the level of our capability of measurement. Now, when does this break down? Well, we know when it breaks down. It breaks down if we look at the phenomena at much smaller scales. We know that if we keep on decreasing the scale, we keep on seeing things that appear stochastic, but they are no longer quite satisfying the same laws we're used to. If you're doing MEMS, microelectronic mechanical systems, you know that you, for instance, don't have a no-slip condition anymore, and that's a reflection of looking at a particularly small scale. Or you can look at phenomena that are larger, but just happen to go slower, such that on the time scale of interest, things evolve slowly. What we obtain in this case falls under the general umbrella of non-equilibrated mesoscale physics. And it covers quite a bit of ground, which is of interest both from the intellectual, theoretical point of view, but also from the practical point of view. We typically find ourselves in the situation that the law of large numbers is applicable, and we can ascertain average behavior. We can ascertain what the means of the behavior should be. We should somehow be able to do a rational prediction. But the central limit theorem itself is not going to be that useful, because though we know that in the limit of large realizations, we're going to go to a Gaussian deviation from whatever we expect between measurements and the mean for whatever quantity, the process is now going to be something which isn't quite at that limit yet. We're going to have probability distribution functions which are not necessarily going to be Gaussian. Such examples are, just to pick a couple, exemplified in the pictures that we have here. One for polymer flow. We have a dilute polymer solution, and the interaction of the, let's say, Newtonian background fluid, which transfers energy to polymers whose microscopic configuration you can think of as a bunch of balls and springs. This interaction to and fro leads to different behavior, and we get what are known as the viscoelastic equations of fluid flow, governed by things other than the Navier-Stokes equations, things like the old droid models. Or another example is that of cellular motility. A cell typically moves by completely reconfiguring its entire skeleton to go to a new place. The skeleton itself is composed of actin filaments that grow, cross-link, attach in various other ways to the cellular membrane. And as seen in the phosphorescent lighting of a particular ARP23 protein that governs this process on the picture on the left of cellular motility, that reconfiguration is what leads to the motion of a particular cell. In both of these situations, what we have is something in which we can't describe the microscopic physics, the polymer configuration when it moves through a sharp contraction in one case, or the cellular configuration of an actin network in the other, by any known a priori probability distribution. Yes, if I had a very long observation time and very many experiments, perhaps you let these things relax, they would somehow tend to some normal distribution. But on the scale of interest that we are looking at the phenomena, the probability distribution describing polymer configurations or actin network configurations are not Gaussian. Of course, if you further decrease your observation scale, you move into deterministic physics, but that's not our interest. Our interest is going to be in this mesoscale regime. So what are the current approaches? Well, we know a bunch of these. A bunch of them are taught. A bunch of them are objects of current research. In the classical realm of what's being taught in a typical physics kinetics course, you have things like the Chapman-Enskog expansion, in which you just do a perturbation expansion of your probability distribution, and you apply methods of applied mathematics and get something which gives you a non-Gaussian distribution to some degree of accuracy within the expansion and the Knudsen number. Or you can, on a more active research front, say that you're looking at a phenomenon and you add a stochastic component, but you apply the traditional method of linear space methods, such as, you enrich your finite element basis for the deterministic part with a stochastic component as an extreme methods, or you have a linear space description of the stochasticity by saying polynomial chaos expansions in terms of some linear combinations of polynomials that take into account stochasticity. Or you can also do things like Bayesian updates, which is very popular in UQ studies. Now, the idea behind what I'm going to be presenting today is to look at a slightly different approach to the problem. We are still going to be in the situation that we're going to think, yes, the phenomena at this mesoscale of physics admits a description through a probability density function. So we're going to say that we're not in the deterministic regime. We still are going to have some stochasticity, but we're not at the level of so many interactions in the volume and time interval of interest that we are definitely going to have normal Gaussian distributions. The probability distribution is going to be assumed to be somehow describable in a parametric form. But we're not going to impose the particular parametric form a priori. We're not even going to know how many parameters enter into the parametric form. We're also going to be interested in the possibility that the parameters that arise in the PDF are going to evolve, perhaps in time, perhaps with some parameter governing the forcing of the system, for instance, such as a Reynolds number within a flow that you accelerate. And the hypothesis that we put forward is then going to be put into a particular conceptual framework. And the conceptual framework, as announced by the title, is that of information theory. Shannon information theory, perhaps familiar to most everybody, but just a brief review, just talks about the reliability of receiving messages over a noisy channel. So we can think of this message as being something that we measure from physics, and it contains information about the microstate of the particular physical system we're interested in. We have a space of such possible measurements in physical language, messages in the language of Shannon, and each one has a particular probability. Associated with the probability, we have an information content, or the self-information. This is the negative log of the probability of a particular message or a particular measurement, reflecting the fact that measurements that you do not expect, those that have low probability, contain large information. The surprise factor is the information in this context. In this light, the average information is, of course, just a sum over the information of each message and the probability within the constraint of normalization of your probability distribution. And it can be interpreted as the uncertainty that you have about the microstate the system is in, or equivalently, the uncertainty in what your next measurement about the system is going to be. To kind of make these things just a bit more concrete, you can set an upper and lower bound on the average information. If you have the maximization of that particular functional with respect to all of the possible probabilities, you come across that the maximum is obtained under the constraint of normalization and nothing else by the equiprobable distribution. The probability is essentially 1 over the size of the system, and the maximum average information, which we'll see as the entropy, is going to be the log of the number of states. And this is things that we are familiar with from statistical physics. The minimum is when you have a certain microstate, namely there is one microstate which has probability 1 and all the other ones have probability 0. And that's the range of our average information about the system. So this is going to be the approach. And in presenting how to work this approach into something workable in the types of applications that I mentioned, we're going to go through a bit of presentation, a synopsis of information theory, and then more importantly, information geometry. Information theory is essentially, as I mentioned, the study of functionals that we can associate with random events. The information, self-information itself is a transformation of a probability. And then if we think about all of the probabilities, we can form various functionals such as the average information, which turns out to be exactly what we understand physically by entropy, or also if we have certain knowledge of the system that is incorporated and you can break it apart into 2 parts, the typical things that we are familiar with, namely joint entropy, conditional entropy, or mutual information. These things are kind of familiar. They satisfy typical things that we are also going to encounter in Bayesian updates of probability distributions. Let's now move on, though, to something which might be a bit more unfamiliar. This is typically not part of the general presentation of differential geometry, though it uses classical differential geometry methods, and namely the differential geometry approach to families of probability distribution. The objective here is that we would like to look at not one particular distribution, but we would like to look at many probability distributions that are parametrized in some way. And we would like to describe the intrinsic geometry of these sets of family distributions. So you have, at this point, the construction of a set of probability distributions in which we have probability distribution for some random variable achieving the value x, and that probability distribution is parametrized by the parameter psi. These parameters psi, there are n of them, we don't exactly know what they are. And this is a structure now that we will make to be a manifold, in the sense that we will assume that there are multiple possible parametrizations, and all of them are of class C infinity, they're smooth, and they're diffeomorphic to one another, they're equivalent. This is the standard introduction of a manifold, because the manifold points in this context are probability distributions. It is called a statistical manifold. And a standard example, of course, would be just a multivariate normal distribution, like we have here, in which we have a multivariate distribution over k variables. And this is described by these parameters, namely k means and a covariance matrix, which can be given in full form as a k by k matrix. We also know, of course, that it has to be positive, definite, and symmetric, so we can make the number of parameters be half of that, essentially. Now, what is going to be our viewpoint? It's useful to keep a very elementary linear algebra picture in front of us, or in the back of our minds, as we go through the generalization to statistical manifolds, namely just standard least squares in linear spaces. Everybody's, of course, familiar with this standard representation. You have a large dimensional vector, maybe some data, you want to express it in a compact form as a linear combination of some basis vectors, and you project down onto the column space or the range of that particular operator that you want to use as your expression for the approximation. This corresponds to least squares and the standard 2 norm, but more importantly, from our point of view, it corresponds to a particular way of thinking of how we obtain that approximation. It's the minimization of a distance with respect to all possible other approximations that would lie in this linear subspace. Of course, the minimization is something that we understand intuitively as just being an application of the Pythagorean theorem and then minimizing the error, making the hypotenuse of that triangle be essentially the single distance corresponding to the orthogonal projection from B down onto the column space of A. We can do this very efficiently, which is why we like it so much. We can do incomplete QR factorizations, come up with a projector, and thereby come up with an approximation. Now, with this in the back of our minds, if we go back to our multivariate Gaussian, notice that our parameters are these psi that are the means arising here, the covariances. They arise inside of the argument of an exponential, and they also get multiplied with one another. So if we want to describe probability distributions such as these Gaussians in terms of these parameters, we're going to have to face the problem that that is no longer a linear relationship. We're going to have to consider what happens when we work on now essentially curved manifolds in which our standard Euclidean geometry has to be modified. We know that this will typically involve the definition of a new metric, which will no longer have coefficients drawn from the identity matrix. They're going to be coefficients that correspond to a scalar product on that particular manifold. We're going to have to then further think about Euclidean distance in our normal space as something intuitive, but what happens if we want to define a distance between probability distribution functions. And then, most importantly for applications, how to maintain efficiency, how to be able to do this in a way that still is something that we can actually work with in practical applications. So now I'll go through a bit of an overview of the differential geometry background, then the approach to constructing manifolds in practical cases, and then finally I'll close with a couple of applications. So before I go into this, I kind of laid out the motivation and the background. Any questions up to this point before I move on?
Yeah, any questions?
Like I said, I can't see anybody. I just see my own presentation, so I want to make sure that it's interactive and I just don't keep on going.
Yeah, yeah.
I have a question.
Great.
So in the case of the statistical manifold defined by those n plus, maybe can bring up the previous slide, please. Yeah, the k plus k choose to this thing, parameters. What is the dimension of this manifold?
In this particular case, we know the dimension. It's going to be k plus k times k minus 1, k plus 1 over 2. It's exactly the number of independent parameters.
Okay, but the points on the manifold are they the collection of these parameters, or are they probability distributions defined with respect to those parameters?
I'm on this manifold of dimension k plus k squared, let's say, to make it easier for me to refer to it. And that means that if I'm at that point, I know what mu and sigma is. Therefore, I know the probability distribution.
Right. Okay, I see. So, and your notion of a distance is how to define not a distance between the parameters themselves, but actually the distributions defined by those parameters.
Correct. That's the essential aspect.
Okay, thank you.
Mm-hmm. Okay. All right. So I'll move on. Now, what makes Euclidean geometry so easy, of course, is that on a flat manifold, if you think about the tangent space to the manifold, it's the same at all points. It's essentially that manifold. If I'm in the plane and I think about the tangent manifold at a point in the plane, it's the plane itself and it's the same everywhere. That does not happen if I'm on a curved manifold, of course. The picture over there is a schematic of the situation in which if I'm at a particular point on the manifold, then the approach of differential geometry is to say, let me look at infinitesimally close points, thereby taking, for instance, the derivatives of the curvilinear coordinates, the parameters of the statistical distribution in our case. These define vectors, and the span of these vectors is a tangent space, which is defined infinitesimally at that point. But of course, the tangent space at one point, if the manifold is curved, is no longer going to be coincident with the tangent space at another point. So if I would like to do any comparison between what happens at two different points, I have to be able to transport a vector from one tangent space back to a reference tangent space. If we think about our standard definition of a derivative, f of x plus h minus f of x over h, we assume that f of x plus h lives in the same space as f of x when we do that particular subtraction. If they would live in different spaces, I'd have to transport it to a common space and then do it in order to do a differential. This is something which is formalized by the notion of a connection. We have to define how we move the direction of these vectors from point to point. And because we're going to be considering very small displacements, this is something which is a linear mapping between the tangent spaces at infinitesimally close points. This is the parallel transport, which is given by the capital P symbol from point P to point P prime, a mapping from the tangent space at point P to the tangent space at P prime. If you do a standard expansion of what the deviation between the tangent vector along one coordinate line is in the old tangent space with respect to the same tangent vector to the same coordinate line in the new one, you get what are known as the connection coefficients. And specifying the connection coefficients, or how you move the tangent vectors of parameter lines from one point to the other, is a specification of how we work on a manifold. Now, you can have, and we'll see in just a bit, multiple connections on the same manifold depending on how you connect points. And the idea is that we can use this to our advantage, as we'll see when we extend our least squares procedure. Finally, what we do when we specify connection coefficients is especially we're generalizing the notion of a derivative. Again, to come back to the elementary calculus example, f of x plus h minus f of x over h, we're assuming that we're moving at the same rate along the x-axis. If we move at some kind of differential rate, we remap the x-axis, then essentially we're going to be doing something which corresponds to a covariant derivative. Now, the essential part that happens when we do the translation of a vector from one tangent space to another is known as parallel transport. And the way that we can carry out parallel transport is basically given by this relationship for the components of a vector. If we think about a curve along which we're doing the parallel transport, this is the law of the transformation of the components of that particular vector, x of index k, and it involves all of the changes along the curve with these scaling coefficients, which are the connection coefficients. When you do the parallel transport of a tangent vector itself, then we get what are known as the geodesic equations. And in the plane, of course, the geodesic equations in Euclidean geometry are just lines, but in other cases, they are different. On the sphere, they are, of course, famously known as the great circles of the sphere. One thing to keep in mind as we move on is that if we do alternative types of connections between the points in a manifold, we will have also different parallel transports. I'll come back to that. Now that we have a notion of how to move things from one point to the other so that we can carry out comparisons, we have to address the problem that was pointed out in the question, namely, okay, each point is a probability distribution, so you're clearly not going to be thinking of doing an Euclidean distance between probability distributions. What does that mean? Neither do you want to do anything like an arbitrary Euclidean distance between the parameters. Yes, it might be expedient, but it has no real meaning. What we would like to do is we would like to think about how the property of interest to us changes. We're looking at probability distributions. Within an information theoretic background, we're interested in the information. So we're going to be interested in how we change the information content as we change the value of a parameter. This is what is shown here as the change with some parameter of the PDF of the information content. Now, if you try to do that, of course, you come across the problem that taking the expectation of that is 0, so that doesn't work. However, as introduced by Fisher, early 20th century, we can introduce a metric based on the idea of measuring the variance of the change in the information. So we're going to be taking the expectation of the second derivative with respect to the parameters. And essentially what we're going to get here is that we're going to be measuring the curvature of the information. And that's going to be our essential quantity that we introduce to replace what would have been the Euclidean distance. With that definition, we can define a metric. It's the Fisher information metric right here. It's going to be the expectation of the change in the information when we move along the ith parameter component times the change in the information when we move along the jth information component. And we are now in a position to have a meaningful concept of what we would understand by distance on a statistical manifold. It now corresponds to the change in information as we move from point to point on the manifold. Here's a simple example. If I just think about the univariate Gaussian, just a single mean and a single variance, we come across a number of features that we will be working with in more complicated applications in a very simple situation. Namely, first off, the univariate Gaussian depends on two parameters. So it lives in what looks like the plane. But the connectivity induced by the dependence of the probability distribution upon the parameters is not that corresponds to Euclidean geometry. We do not have d mu squared with a 1 coefficient and d sigma squared with a 1 coefficient. Both of them have a coefficient that varies as the inverse square of the variance. So if you work this out, the geodesics that correspond to the univariate Gaussian statistical manifold are those that we encounter in what is known as the upper Poincare half plane. They are ellipses or arcs of ellipse and lines. So whereas in the plane I would move along a straight line in order to come to the shortest distance between 2 points, in the Poincare half plane I have to move along ellipses or straight lines. On the horizontal axis over here we have the mean. On the vertical axis we have the variance or the standard deviation. Now this makes problems of extending our concept of model reduction from least squares a bit more difficult. Notice that when we were doing this in linear spaces, we knew that we could just take the orthogonal projection. We knew the direction that we would have to go on is orthogonal to the subspace. In our case, again, we have to end up at a best approximation, which is going to be orthogonal to the subspace, but we're going to have to do transport on a curve. And this transport of a curve now transforms the problem to a boundary value problem, which is much more difficult to do, especially as the dimensionality of your statistical manifold increases. Essentially, you can have to think about this as having to go from a point P, try a curve, figure out what the angle is here. If it's not 90 degrees, modify your starting direction, and so on, much as in a shooting approach to solve a boundary value problem by solving an equivalent initial value problem.
We have a question from audience.
Yes, please.
Sorry.
Yeah.
Yeah.
So how does the geodesic, this distance induced by the Fisher, say, this thing metric, compare Fisher information compared to the something like Kullback-Leibler distance between two distributions? There must be a connection, right?
Well, I'm going to be going to that when we generalize. They're not that connected because the Fisher information metric is a true distance. And as you, of course, well know, the Kullback-Leibler is a semi-distance, right? It's a divergence. It doesn't satisfy the axioms. And the idea now is which one is going to be more appropriate to answering a particular question. If we have, as I'll show in a simple example in just a bit, a pretty good idea of our phenomena, and then we want to do a minimal modification of our model, we can think of that as saying, well, I would like to do the minimal modification of the PDF consistent with some constraints. I'll be using the Fisher information metric. If, on the other hand, I want to do a model reduction, we'll see that the Kullback-Leibler or some other equivalent divergences play an important role because they will allow us to do a computationally efficient generalization of the Pythagorean theorem. So they're not the same. And if you use the Fisher information metric for your model reduction, you're going to always come across this problem of having to solve a boundary value problem, very expensive computationally. Otherwise, if you adopt something which relaxes the axioms, the properties we impose on our measure of a discrepancy, do a semi-distance instead of a distance, such as the Kullback-Leibler divergence, we're going to be able to do something which is an efficient Pythagorean theorem.
Okay, and that Pythagorean theorem is presumably connected to Bregman divergences, right?
Yes, it's something which is formulated in what we'll see as the language of dual connections, and they can be seen as particular cases of a Bregman divergence. Yes.
Okay, thank you.
With different generating functions, of course.
Yeah, of course. Yeah, got it. Thanks.
So, simple example to kind of follow up on what we did. Yeah, suppose that I do an experiment and I measure stuff and I get statistical estimates through some statistics of the mean and the variance. But I know by physical constraints that the mean has to have some value. This is very usual in most situations. I can do a big molecular dynamics. I have some stochastic variance in that from a thermal reservoir, but I know that I want to impose that the first 3 moments of my distribution have to correspond to mass, momentum, and energy. Well, if I have such a constraint, this is very easily shown here. Suppose that I have my known mean be minus 1 for argument's sake. And when I did my measurements, I got this particular value over here. How do I transfer my estimate of the probability distribution from my statistical estimates to my constraint? I definitely should not just say, oh, I go ahead and change one of the parameters to the constraint. What I should do is to do the geodesic transport, which in this particular case would correspond to moving along a particular ellipse, to move from one value of the mean to another value of the mean, appropriately changing the variance such that we do the minimal change in the Fisher information metric. This is the kind of thing that we'll be looking at consistently as we move to more complicated applications. Another way that we can use this, in very simple guys, I'll just zoom through this application, is that if we have an active particle moving through a medium and it eats away at the medium, think bacterium in a medium in which it's feeding, you have this kind of flight forage behavior in which it executes a local Brownian walk with Gaussian random steps when the feeding is good, and then when it gets poor, it takes a big step, as shown by these jumps over here. This is something that we typically describe through a Levy distribution. And if you run a bunch of stochastic simulations of these, you get very, very many trajectories. And you can ask yourself, well, okay, what does the overall time dependence of the variance look like? How do I collapse all of those things? And you can do the same thing to come up with this particular curve here, which is actually a verification of what we know from experiments of this type. And in this case, if you would have just done things like simple averaging of the stochastic, the distributions of sigma at various realizations of the process, you would not have gotten the curve that corresponds to what we see in experiments. Coming back now to the general presentation, let's think about the analytical framework for some of the more common families that we encounter. This is what Amari's work was on, basically to recognize that the most important statistical distributions that we encounter in practice, namely those that have to do with the exponential family and the mixture family, are things that you can describe analytically. And here's the linchpin of this entire theory, namely, you can describe them in a computationally efficient way through connecting points in 2 different ways. You can define 2 connections which are dual of one another, 2 ways of connecting points, namely vectors between tangent spaces. And then, as was foreshadowed by our discussion previously, if you relax your definition of what you mean by distance to a semi-distance, you can then formulate the equivalent of a Pythagorean theorem. Namely, if I move from one probability distribution to another, R, it can be as stated as the divergence from that probability distribution to an intermediate one, and then the intermediate one to the second. Furthermore, and this is the interesting aspect that was pointed out by Amari, you can, in the dual connections, render all of the important statistical families be flat in one of the coordinates. So all of a sudden you can, if you do one of the coordinate systems, have the property that you don't have to go along a curve, you can go along a straight line to be orthogonal to a surface. The penalty that you pay is that by contradistinction to least squares, you have to always do changes of coordinates. And those changes of coordinates are known, they're been published by Amari and so on. But it allows you now to efficiently think about the generalization of least squares to curvilinear families of statistical manifolds. Let's now move on from that overall analytical framework to something which is of interest to us, namely, how do you do computation with all of this? Well, computationally, we're really limited in what we have that is efficient. The workhorse is, of course, the SVD. And we know what it corresponds to. It's going to give us something that is a local Gaussian approximation of the statistical manifold. So the picture that I would like to present to you is the following. I have a system. If I gather data about the system over some subinterval of the evolution time, I can definitely figure out an SVD of that data, which I can think of as a local Gaussian approximation to some underlying statistical manifold, which I do not yet know. That underlying statistical manifold is assumed for mesoscale physics to actually be something which does not correspond to a Gaussian. So the situation you find yourself in is kind of something suggested by this picture. You have a bunch of shapes of known form. In our case, they would be hyperellipsoids. And the envelope of that is the manifold that you want to work on. The difficulty that you have now is that you do this at discrete times. You don't know the underlying dimension of the manifold, and you have to somehow figure all of this out. I'll go through an overview of how this is being done. It's an overview due to time constraints. Can't possibly go through all of these details, but I'm glad to talk with anybody that's interested. Essentially, you have a point cloud that correspond to various PDFs, each of them a local Gaussian approximation. And then we use the idea of nested complexes and persistent homology to figure out the intrinsic dimension of the underlying manifold. This is something which is being used in a bunch of applications, and I'll probably not go more than hand wave about it. Essentially, there's a rational way in which, as we increase the connectivity between the points and the complexes, that we can come up with an idea of what the most probable dimension of the underlying manifold is. This is something that is typically shown as these persistence diagrams and barcode diagrams. And once we have that, working on that manifold, we say, okay, we want to build a local parametrization. A local parametrization is something that we can do in a piecewise linear fashion by just doing simplicia in high dimensions. And at any given node, we have a discrete evaluation of the curvature just by all of the faces of the simplicia that have that node as a common vertex. So we can include all of the information that we get from SVDs acquired during the simulation into a representation of an underlying manifold. Let me present a couple of applications of these ideas. Again, in the interest of just showing the flavor of where this might lead to. One is a rather straightforward application to something probably familiar to most people, a way to do lattice boltzmann or lattice methods in general. And the other one is going to be a much more involved application that has to do with biomechanics. Lattice boltzmann, briefly go over it. That's the Boltzmann equation. Our expansion we get at various orders, Euler, Navier-Stokes, Burnett. And the way that we get those is by just computing those moments to get the various kinds of approximations. What is the linchpin of a lattice-Boltzmann method? You discretize the velocity space, and you then carry out the streaming step in which you move particles to lattice sites. But then you have the problem of modeling collision. And collision is the recognition that at the kinetic level, you're not necessarily at equilibrium. Now we're in the framework that we are interested in of a mesoscale phenomena that is non-equilibrated. So how can you approach this? Well, the standard way, which is in most lattice-Boltzmann simulations, is to say, well, it kind of relaxes at some time. And this is the BGK single relaxation time, which you can then finesse into something a bit better by introducing multiple relaxation time for various moments that correspond to mass, momentum, energy, and so on. Both of these, though, are known to be highly restrictive in terms of the flows that they can describe. They can't describe high Mach or high Reynolds flow. And the reason is that you have a very simple representation of the relaxation. The way that you can alleviate these restrictions that lead to either the necessity of very large computational time or very fine grids that is suggested by what we've done in the framework we have goes as follows. Well, you have data. You have data from your current state of the microscopic system. And then what you would like to do is, instead of going along the BGK path in a straight line from your current approximation to where you want to arrive at the equilibrated, you construct a manifold of probability distributions and generate a geodesic on that path. The amount of distance that you travel on the geodesic is something that is immediately related to the time step and the viscosity of the fluid that you have. And this then allows you to rapidly compute with no instability things like the speed at Reynolds numbers up to 10 to the 5 or so we've achieved, and Mach numbers in the low range, but low supersonic range, but up to Mach 2. Another application, which now involves multiple levels, is going to be suggested by biomechanics. This is joint work that involves a number of people here at UNC, in which we have brain tissue that is subjected to trauma, and we're interested in how that trauma imposed by impacts at the macro scale reflects into micro tissue. And the idea here is that the micro damage is done at the level of individual axons within the brain. So you have to move from a continuum model for a stochastic medium to a representation of the medium as being a bunch of fibers connected to one another, and then the fibers themselves being composed of microtubules that themselves have a stochastic structure based upon the molecular dynamics of alpha and beta tubulin. This is an application in which we apply the framework at various levels. I'll briefly glance over and leave more time for questions if possible. Namely, within a hyperelastic framework that corresponds to the continuum behavior, your main question is, what is the constitutive law that relates stress to deformation? And that is something that you can come up with by including all effects, the elastic and the viscous effects, and then doing instantiations of the measurements that, or doing realizations from measurements, and then applying our framework to come up with a constitutive model, which is data-driven. Essentially, all of the data that we get from measurements are assumed as data points that lie on a manifold, and then we go to the minimal such model in order to come up with something that now closely fits the data, red line going through the data points that we have. Same approach then applies if you want to do things like, what is the probability distribution orientation of fibers within the brain? Because these, though they have a general orientation imposed by the brain structure, also have variability in how that particular orientation is realized. And finally, if you look at the structure of the neurons, they have this axon over here. And the axon in cross-section is just a bunch of microtubules that you would like to find the mechanical properties of in order to be able to figure out when they break. So same principle, you have a stochastic simulation, this time it's given by molecular dynamics, and you want to do a reduction of that to something which is amenable. We have a publication on this done at 0 temperature, and we've extended this now to non-zero temperature by the methods that we've outlined up to this point. Then same principle applies to probability distribution for fiber orientations. At the end of the day, allowing you to do, and I'll close with this, predictions of where you get individual axons breaking by combining these three applications of the information framework approach to model reduction, namely at the continuum level in order to find constitutive parameters, at the mesoscale level to determine fiber networks of neurons, and at the microscopic level to determine mechanical properties of microtubules, to the point that if you combine all of those, you do come up with a prediction of where axons break that are matched qualitatively, at least. We're always happy with qualitative as the first thing, with what you get from staining measurements. And with that, I'll acknowledge support, and hopefully everybody has a glimpse into the workshop over here. And please ask questions or suggest things that you would like to talk about in collaborations or just brainstorming. Thank you so much.
Thank you so much, Soren. That was a wonderful talk and very informative. All right, let's have a Q&A session. And yeah, pause. Anyone has a question, please unmute yourself and then ask questions. No questions? Any other applications can you mention other than the one you have showed so far today?
Yeah, we're doing fracture in the same framework.
Mostly the medical applications. Yeah.
No, fracture is for applications with these are military applications. So
oh, I see.
Spoliation fracture, high kinetic impact. Other situations in which you are very far away from equilibrium when you do the simulations and you can't trust your constitutive model.
Mm. Very cool. These days, the people try to apply the machine learning to come up with the unknown constitutive law as well.
Yeah, there's also an interesting link between machine learning and all of this. I didn't go into that, but the weights that you have on a deep neural network, you can interpret them as stochastic processes, and it turns out that the stochastic gradient descent procedure kind of corresponds to a information minimization on the stochastic process parameters.
Yeah, right. All right. Any questions from audience? If not, let's thank our speaker today, Soren. And thank you so much for the wonderful talk, Soren. And as Soren mentioned, if you have any idea of the potential collaborations, please let Soren know. That's kind of one of the main motivation for this the seminar series and the workshop. So
yeah, I had a lot more details, but I prefer just to raise everybody's interest. So.
Yeah, you did a good job on that. Yeah.
All right, thank you.
Thank you, Soren.
Okay.
Okay, so let me push the stop button.